The light is overwhelming at first, so bright it feels less like illumination and more like pressure, as if photons themselves have grown heavy. Beneath that relentless glow, a gas giant hangs impossibly close to its star, locked in an orbit tighter than anything our solar system would ever allow. From this distance, the star fills a quarter of the sky, not a gentle disk, but a roaring, turbulent furnace. Its surface boils with convection cells the size of continents, each one rising and collapsing in minutes. And circling just beyond the reach of those blazing prominences is a planet that should not exist. Clouds here do not drift, they seethe. They stretch like metallic ribbons across a sky heated to more than 1,500 degrees Celsius, about 2,700 degrees Fahrenheit. The atmosphere glows faintly, as though the entire planet is being backlit from within. You're descending through it now, slowly, carefully, feeling the rising temperature as molecules gain speed, collide more violently, and release their stored heat into the gas around you. Hydrogen and helium dominate the mix, the same ingredients that built Jupiter, but here they behave differently. Under irradiation, this intense, even stable molecules, such as water or methane, struggle to survive. They break apart, recombine, and sometimes vanish entirely from the spectrum that astronomers use to analyze them. Below you, deep in the haze, winds race from the blistering day side to the night side at several kilometers per second, fast enough to circle the entire planet in less than a day. If you could stand in this atmosphere, which you cannot, the sound would be unimaginable, a constant, roaring movement of hot gas trying to equalize temperatures that refuse to balance. Pressure rises as you descend, density increases, and soon the world below starts to take shape. A turbulent, shifting globe bathed in perpetual, merciless daylight. The star overhead sits only a few million kilometers away. For comparison, Mercury orbits the Sun at about 58 million kilometers, or roughly 36 million miles. This world has no such luxury. It might complete an orbit in just a few days, sometimes even in a matter of hours. Its year is shorter than a weekend. From its surface, if it had a solid surface at all, the parent star would appear so close that the idea of night becomes almost ceremonial. Most hot Jupiters are tidally locked, so the same hemisphere always faces the star, roasting day after day with no rotation to spread the heat. The night side, though shielded from direct radiation, is still warmer than the hottest deserts on Earth because the superheated winds never really stop. It wasn't long ago that astronomers assumed such a planet was impossible. Before the mid-1990s, gas giants were expected to form far from their stars, beyond what's called the ice line, where temperatures are low enough for solid ices, water, methane, ammonia to collect and build large planetary cores. Everything we knew came from the architecture of our own solar system. Jupiter, the archetype, sits comfortably at 5 astronomical units from the Sun, its orbit slow, its environment cold. And so the earliest models of planet formation were built to make Jupiters, but not like this. Then, in 1995, a planet named 51 Pegasi b appeared in the data. It orbited its star at just 0.05 astronomical units, closer than Mercury, completing a full orbit in about 4 Earth days. Michel Mayor and Didier Queloz detected it through tiny shifts in the star's motion, wobbling back and forth due to the planet's gravitational pull. That wobble revealed something massive, roughly half the mass of Jupiter, circling a sun-like star in a scorchingly tight loop. The discovery overturned decades of expectation. If gas giants like this existed, the universe was far stranger and more inventive than anyone had predicted, and the strangeness didn't stop there. As more planets were discovered using radial velocity surveys in the late 1990s and early 2000s, hot Jupiters began to appear regularly. Some were larger and puffier than Jupiter, their radii expanded by the heat from their stars. Others were denser, compressed by gravity into compact spheres of exotic gas under extreme pressure. A few orbited in retrograde, moving opposite the rotation of their host star, an arrangement that defied everything known known about how planetary systems ought to form from a rotating disk of gas and dust. This descent continues, the atmosphere growing thicker and hotter as the gas giant's profile warps beneath you. At this altitude, the bright blue glow is not a true colour, but a scattering effect, superheated particles interacting with relentless radiation. Temperatures here can exceed 2,000 degrees Celsius, about 3,600 degrees Fahrenheit, in the most extreme worlds known as ultra-hot Jupiters. At those levels, even molecules such as titanium oxide or aluminum oxide may exist in vapour form, drifting in an atmosphere where chemistry behaves like it's taking place inside a furnace. Some of these planets swell to 1.5 times Jupiter's radius, while maintaining similar mass, meaning their density becomes astonishingly low, less than water in some cases. Others become tidally stretched, elongated slightly by the gravity of their nearby star. Infrared observations from telescopes such as Spitzer and now jwst allow astronomers to map temperature differences across their surfaces. Some planets show hotspots shifted eastward from the expected substellar point, pushed by the furious equatorial winds. The ground never appears because there is no ground, only deeper layers of gas compressing under their own weight, transitioning eventually into metallic hydrogen, a form of matter that exists at such immense pressures that electrons flow freely, behaving like a metal. Lightning may spark through this huge convective zone, though on a scale vastly greater than anything Earth experiences. Thunderstorms on Jupiter can be thousands of kilometers across, or thousands of miles. Here, with additional stellar heating driving violent circulation, they might be larger still. Before the heat overwhelms your instruments, you get one final glimpse upward. The star dominates almost everything. Its radiation so intense that parts of the upper atmosphere stream away into space. Some hot Jupiters have been observed shedding mass in great comet-like tails, hydrogen escaping from the gravitational hold of the planet, pushed outward by stellar winds and ultraviolet light. This loss can reshape the planet over billions of years, reducing its mass or even stripping its outer layers entirely. This is a world that redefines expectations, a world so close to its star that the ordinary rules of planetary behaviour fall apart and reform into something new. And yet these planets are not rare, they are among the easiest exoplanets to detect. Their existence forced astronomers to rethink how planetary systems form, how planets move, and why our solar system looks the way it does. These boiling giants rewrote planetary science not by being exotic outliers, but by being common enough to suggest that nature builds planets in ways our early theories never imagined. The story begins quietly, with a star that did not appear unusual, 51 Pegasi. In the constellation Pegasus is a middle-aged sun-like star about 50 light-years away. For decades, it was simply another point of light in a crowded stellar neighbourhood, giving no outward sign that anything exotic was orbiting it. In the early 1990s, astronomers had been searching for exoplanets for over 30 years, with no confirmed detections around sun-like stars. The silence was almost embarrassing. Telescopes improved, spectrographs were redesigned, and yet the cosmos seemed reluctant to reveal whether our solar system was typical or an oddity. Michel Mayor and Didier Queloz, working at the University of Geneva, were not searching for something dramatic. They were being methodical. Their tool was a high-precision spectrograph at the Haute-Provence Observatory in France, an instrument capable of measuring the subtle shifts in a star's light as it moves toward or away from Earth. These shifts, known as radial velocity variations, arise when an orbiting planet tugs on its star, pulling it slightly in different directions. The effect is small. For a Jupiter-like planet orbiting at Jupiter's distance, the Sun's motion is only about 12 meters per second, roughly the speed of a slow bicycle. Detecting motion that faint across tens of light-years requires extraordinary stability and patience. Mayer and Queloz were looking specifically for large planets. Gas giants produce measurable stellar wobbles, making them the first logical targets. but they expected to find them far from their stars, just like Jupiter and Saturn. The classical model of planet formation, rooted in studies from the 1970s and 1980s, held that giant planets could form only beyond the ice line, perhaps several astronomical units from their stars. Any planet too close would be unable to accumulate the necessary ices and gases to form a giant. So the search strategy was simple: observe stars over long stretches of time, watch for slow, gentle oscillations, and hope something significant emerges. Then came the signal from 51 Pegasi. At first glance, it didn't make sense. The radial velocity curve rose and fell with a period of just 4.2 days. That implied that whatever was orbiting 51 Pegasi completed a full orbit in less than a week. To cause a star to wobble with that frequency, the planet had to be extremely close, at a distance of around 0.05 astronomical units, or about 7.5 million kilometers. That's about 4.6 million miles. Far closer than Mercury is to the Sun. Closer than any theoretical model said a gas giant could exist. Worse, or more intriguing, depending on perspective, the amplitude of the signal suggested the companion had a mass roughly half that of Jupiter. Too small to be a star, too large to be anything but a planet. But how could a Jupiter-mass planet orbit so close without evaporating? How could it have formed there? The data felt like a contradiction. When Meyer and Queloz first presented their findings at a conference in Florence in October 1995, reactions ranged from excitement to skepticism. Some astronomers suspected the star might be pulsating, altering its brightness and spectrum in a way that mimicked planetary influence. Others thought it was an instrument error, yet the signal repeated predictably, with perfect periodicity, matching exactly what a gravitational influence should produce. There were no irregularities, no chaotic deviations. Something was orbiting the star, and it was massive. Radial velocity detections rely on the Doppler effect, the stretching or compression of light depending on motion. When a star moves toward Earth, its spectral lines shift slightly toward blue wavelengths. When it moves away, they shift toward red. The shifts are minuscule, often less than a meter per second, but with modern spectrographs, they become detectable. For 51 Pegasi b, the motion was stronger, roughly 56 meters per second. Still small on cosmic scales, but unmistakable. The pattern was stable enough that it couldn't be caused by star spots or magnetic cycles. Those phenomena produce irregular or slowly evolving signals. This one behaved like a metronome. Meyer and Queloz published their discovery that same year, and the astronomical community re-evaluated its assumptions almost overnight. The prevailing belief that planetary systems should look broadly similar to ours was suddenly under pressure. If hot Jupiters existed, then the architecture of planetary systems was far more diverse than expected. Either these giants formed close to their stars, which defied the physics of early disks, or they had moved inward after formation. The second possibility, migration, opened an entirely new domain of planetary dynamics. 51 Pegasi b forced theorists to rebuild their models. Theories of disk-driven migration had been discussed, but largely as conceptual possibilities. Now they needed to be studied seriously. Simulations began to explore how a giant planet embedded in a protoplanetary disk might spiral inward due to gravitational interactions with the disk's gas. Others proposed that planets might be scattered inward by gravitational encounters with siblings. Chaotic planetary pinball. Suddenly, textbooks needed revision. In the meantime, observational astronomers across Europe and the United States began pointing their spectrographs at nearby stars to verify whether this discovery was a bizarre anomaly or the first glimpse of a new category of planets. Within a year, multiple other hot Jupiters were detected. The pattern was undeniable. Not only did such planets exist, there were many of them. Their short orbital periods made them easier to detect than distant analogues of Jupiter, which require years of observation. So the early exoplanet catalogue became disproportionately populated by these giant, smouldering worlds crowded against their stars. 51 Pegasi b itself became iconic. It was later nicknamed Dimidium, Latin for half, referencing its half Jupiter mass. In 2019, Meyer and Queloz were awarded the Nobel Prize in Physics for this discovery, recognized for opening an entirely new frontier in astronomy. In hindsight, the detection looks straightforward, the data are clean, the curve is elegant. But at the time, the idea of a gas giant in a 4-day orbit was almost absurd. The discovery reshaped the scientific landscape so rapidly that older theories of planet formation now read like incomplete drafts of a larger story. Astronomers had believed that planetary systems would be orderly, symmetrical, perhaps even polite. But nature proved otherwise. The universe produces worlds that challenge assumptions, break rules, and force us to confront our limited expectations. Hot Jupiters were the first reminder that our solar system is not the template. It's merely one arrangement among countless possibilities. When astronomers describe a planet as a hot Jupiter, they're not being metaphorical. The category is literal, a class of gas giants similar in mass and composition to Jupiter, but situated so close to their host stars that their temperatures soar to extremes Jupiter could never withstand. The idea is simple on paper, but in practice the definition involves a combination of mass, radius, orbital distance, atmospheric structure, and thermodynamic behavior that turns these worlds into laboratories of exotic physics. A hot Jupiter typically has a mass somewhere between about 0.3 and 10 times that of Jupiter. This broad range covers planets slightly smaller than Saturn, up to giants bordering the threshold of brown dwarfs. But mass alone isn't enough to define this group. What truly sets them apart is their proximity to their stars. Most orbit within 0.05 astronomical units, less than 5% of the Earth-Sun distance. That's closer than Mercury, which orbits at 0.39 astronomical units. A hot Jupiter can circle its star at distances as small as 0.02 astronomical units, or roughly 3 million kilometers, about 1.9 million miles. At that distance, stellar radiation is not just intense, it dominates the entire energy budget of the planet. Jupiter, by contrast, sits peacefully at 5.2 astronomical units, more than 100 times farther from the Sun than a typical hot Jupiter is from its star. The difference in incident radiation is not a factor of 10 or 100, but thousands. Jupiter absorbs only a small amount of heat from the Sun, with much of its temperature structure determined by internal heat left over from formation and slow gravitational contraction. A hot Jupiter, however, lives under the constant blaze of its star's radiation, making internal heat almost irrelevant. Everything from atmospheric chemistry to wind patterns to the shape of the planet itself is sculpted by the external forcing of intense stellar irradiation. These worlds complete orbits astonishingly quickly. While Jupiter takes nearly 12 Earth years to complete a single revolution, a hot Jupiter's year may last only a few days. Some finish an orbit in less than 24 hours. The physics of such tight orbits lead to a near inevitability: tidal locking. The same gravitational phenomenon that keeps the Moon facing Earth in the same orientation occurs on a much more extreme scale for hot Jupiters. Tidal forces distort the planet slightly, stretching it into an oblate shape and slowing its rotation until one hemisphere perpetually faces the star. This locked configuration divides the planet into two extreme domains. The day side is exposed constantly to intense stellar energy, heating it to temperatures ranging from 1000 degrees Celsius to above 3000 degrees Celsius. Roughly 1,800 degrees Fahrenheit to over 5,400 degrees Fahrenheit. The night side, in contrast, receives no direct radiation and can cool significantly, But the heat imbalance does not remain localized. Strong atmospheric winds, driven by temperature gradients and Coriolis forces, attempt to redistribute the energy. In many hot Jupiters, the winds are so powerful they can reach speeds of several kilometers per second. For comparison, Earth's strongest jet streams reach around 100 meters per second or 220 miles per hour. Hot Jupiter winds can be dozens of times faster. The result is a fascinating temperature structure. Infrared phase curves obtained from telescopes such as Spitzer and jwst reveal that the hottest point on the planet is sometimes not directly under the star as expected, but offset to the east. This hotspot shift is produced by equatorial winds that transport heat before it can re-radiate. In some planets, the shift is small. In others, it is dramatic. The night side often remains warm, hundreds to thousands of degrees, because the continuous circulation prevents it from cooling efficiently. To make sense of these temperature differences, it helps to consider the planet's energy balance. A hot Jupiter's day side absorbs an extraordinary flux of energy, often exceeding hundreds of thousands of watts per square meter. Jupiter, by comparison, receives only about 50 watts per square meter from the Sun. The energy deposited in a hot Jupiter's upper atmosphere heats it so strongly that molecules may break apart. Water becomes dissociated into hydrogen and oxygen ions. Methane converts into carbon monoxide. In some ultra-hot Jupiters, even nitrogen or metal-bearing molecules cannot survive the heat of the day side. Observing these chemical fingerprints is one of the major achievements of modern exoplanet science. Through a method called transmission spectroscopy, astronomers can watch starlight pass through a planet's atmosphere during transit. The atmosphere absorbs different wavelengths depending on its composition. By analysing these absorption features, scientists piece together the chemistry and temperature of the gas at various altitudes. The technique has revealed not just water and carbon monoxide, but also exotic species such as titanium oxide, vanadium oxide, and ionized metals. In a few cases, even iron has been detected as vapor. Jupiter, in contrast, contains ammonia, methane, and water vapor in equilibrium conditions that remain largely unaffected by the sun's radiation. Its deep atmospheric layers transition into metallic hydrogen, but the region where sunlight penetrates is much cooler and more chemically stable. Hot Jupiters represent the opposite extreme. Intense heat from above drives the atmosphere outward, creating inflated radii in some cases. The most extreme examples can reach up to 1.8 times Jupiter's radius, despite similar mass. This low density has puzzled researchers for years. Multiple theories exist. Ohmic heating, tidal dissipation, or the absorption of stellar radiation in high-altitude hazes could all contribute to radius inflation. But no single explanation fits every observed case. Radius inflation is not the only unusual consequence of extreme irradiation. The upper atmosphere can expand enough that hydrogen escapes into space, forming long, comet-like tails. In planets such as HD 209458b, ultraviolet observations revealed a cloud of escaping gas larger than the star itself. The escape rate depends on the planet's gravity, atmospheric composition, and the star's ultraviolet flux. Over billions of years, a hot Jupiter might lose a significant fraction of its mass. Some astronomers speculate that small rocky planets found extremely close to their stars may be the remnants of once massive giants stripped down to their cores. Even the colour of these planets can vary with temperature. Some appear dark because their atmospheres absorb most of the incoming radiation rather than reflecting it. Others exhibit reflective silicate clouds or layers of metallic compounds. At temperatures above about 2,500 degrees Celsius, roughly 4,500 degrees Fahrenheit, traditional cloud formation ceases on the day side, producing clear, almost glass-like atmospheric layers. On the night side, however, temperatures drop enough for materials to condense. Models predict that clouds of silicates, corundum, or iron may form on the dark hemisphere. In extreme cases, these particles may be lofted into high-altitude winds and carried back into the dayside before evaporating, creating a chemical cycle completely unlike anything seen in the solar system. Despite the diversity of these planets, several traits unify them. They are close-in gas giants with short orbital periods, high irradiation levels, and strong atmospheric circulation. Their temperatures can exceed the melting points of many terrestrial materials. Their atmospheric chemistry is driven by photodissociation and recombination under intense ultraviolet and visible light, and they provide astronomers with an opportunity to study planetary physics under conditions that would be impossible to reproduce in a laboratory. The contrast with Jupiter underscores just how unusual hot Jupiters are. Jupiter's cloud layers are cold enough for ammonia ice to form. Its upper troposphere sits at around minus 145 degrees Celsius, about minus 229 degrees Fahrenheit. Hot Jupiters, by comparison, host atmospheres so warm that atoms are ionized. Their thermal structures extend far higher, producing large-scale heights, meaning their atmospheres are puffier and easier to observe during transits. This makes them some of the best targets for detailed atmospheric characterization. Orbital distance is the defining trait. A threshold around 0.05 astronomical units marks the space where stellar flux becomes dominant, gravitational interactions intensify, and tidal forces lock the rotation. Below this distance, the star's magnetic field and wind interact strongly with the planetary atmosphere. Cyclotron radiation, magnetospheric compression, and even induced electric currents may affect the interior structure of the planet. At extremely close distances, less than about 0.02 astronomical units, the star's gravity can begin to destabilize the orbit. In some cases, orbital decay has been detected, with the planet gradually spiraling inward as angular momentum is transferred to the star's rotational motion. These physical characteristics make hot Jupiters more than a category. They are natural experiments, controlled by the geometry of their orbits and the physics of intense irradiation, revealing how gas behaves under extreme conditions. Their study continues to refine models of atmospheric dynamics, chemical equilibrium, and planetary evolution. Though discovered only a few decades ago, hot Jupiters have become foundational to exoplanet science. They are large, bright, and obligingly close to their stars, offering astronomers the clearest window into planetary atmospheres outside the solar system. And through that window, the field has uncovered not just new kinds of planets, but new regimes of physics that challenge our understanding of how worlds form and evolve. When astronomers first confronted the reality of hot Jupiters, the obvious question rose immediately. How could a giant planet form in a place where giant planets should not exist? The early models of planet formation, developed throughout the late 20th century, provided two main frameworks: core accretion and gravitational instability. Both were designed to explain the architecture of our solar system, and both broke down when forced to account for a gas giant pressed against the blazing surface of its star. The core accretion model had been the dominant theory for decades. It described planet formation as a slow and deliberate process. Tiny dust grains in a protoplanetary disk collide and stick together, forming centimetre-sized pebbles, then metre-sized bodies, and eventually kilometre-sized planetesimals. Over millions of years, these bodies grow by accreting material from their surroundings. Once a solid core reaches roughly 10 Earth masses, a threshold determined by detailed modelling of gas capture, it begins pulling in large amounts of hydrogen and helium from the disk, swelling into a gas giant like Jupiter or Saturn. But this mechanism only works in regions of the disk where solid materials can accumulate efficiently. The inner regions of a forming star are far too hot for water, methane, ammonia, or carbon dioxide to exist as solids. Ices, which represent the bulk of solid mass available for giant planet cores, vaporize at high temperatures. Only refractory materials such as silicates and metals remain. and these account for just a small fraction of the disk's mass. In the region within about 1 astronomical unit, far beyond the orbital distance of a hot Jupiter, the temperature is too high to permit rapid core growth. Without ices, core accretion stalls. There is simply not enough solid material close to the star to build a giant planet core before the disk disperses, typically within 1 to 10 million years. Even if a core could grow there, the surrounding gas would likely have been heated and blown away long before the planet could accrete it. The gravitational instability model offered a dramatically different route. In this scenario, the disk itself becomes unstable. If it is massive enough and cool enough, spiral arms or clumps can collapse directly under their own gravity, forming giant planets in a matter of thousands of years. This pathway avoids the need for a solid core entirely, producing planets through the rapid fragmentation of the gaseous disk, much like stars form. But gravitational instability also requires conditions that do not exist close to a star. The inner disk is too hot, too tightly bound, and too dynamically stable for gravitational collapse. Models show that fragmentation can occur only in the outer regions of the disk, typically beyond tens of astronomical units. Once again, hot Jupiters defied the constraints of both known formation pathways. The conflict between observation and theory became increasingly sharp as more hot Jupiters were discovered. Dozens of planets were being found in orbits that the physics of planet formation simply did not allow. The tension grew until the field began to accept an uncomfortable possibility. These planets may not have formed where they are today. They must have moved. Something in the early life of these planetary systems transported giant planets from the cool outskirts to orbits skimming the edges of their stars. The idea of planetary migration was not entirely new. Simulations in the 1980s had shown that planets embedded in a protoplanetary disk could exchange angular momentum with the gas around them. In the simplest picture, waves generated in the disk by the planet create torques that cause the planet to drift inward or outward. But before the discovery of hot Jupiters, these effects were considered secondary, relevant, but not central. Our solar system did not appear to show signs of major rearrangement, at least not dramatic inward spirals of Jupiter-like planets, so migration was assumed to be modest. The discovery of 51 Pegasi b forced scientists to revisit those assumptions. Disk-driven migration became a leading possibility. In this process, a giant planet forming beyond the ice line interacts with the surrounding gas. The gas exerts torques on the planet, causing it to lose angular momentum and spiral inward. Depending on the mass of the planet and structure of the disk, this can happen rapidly, sometimes in less than 1 million years. Suddenly, a mechanism existed that could, in principle, deliver a giant planet from several astronomical units down to a fraction of 1, placing it within the scorching regions where hot Jupiters are observed today. But disk migration alone did not solve every puzzle. Some hot Jupiters have highly inclined or even retrograde orbits relative to their star's rotation axis. Disk migration cannot easily flip a planet's orbit. It typically preserves alignment. This led to another class of theories involving dynamical interactions. A planet's orbit can be altered dramatically through gravitational encounters with siblings, other massive planets, or through perturbations from distant companions. One mechanism, known as Kozai-Lidov oscillations, involves a distant companion in a highly inclined orbit. Its gravitational influence can cause a gas giant's orbit to oscillate in eccentricity and inclination. During periods of high eccentricity, the planet swings dangerously close to its star, where tidal forces act to circularize the orbit into an extremely tight configuration. The final product looks exactly like a typical hot Jupiter, close in, circular, often misaligned and tidally locked. Dynamical scattering provides another pathway. In a young planetary system, multiple giant planets can form and then interact strongly as the surrounding gas dissipates. These interactions can eject planets into interstellar space, send them plunging inward, or thrust them onto erratic, unstable trajectories. If a giant planet is thrown inward far enough, tidal interactions with the star can again circularize the orbit, producing a hot Jupiter. Thus, by the late 2000s, the scientific community had arrived at a realization. Migration is not a single process, but a suite of mechanisms. Some planets probably migrated smoothly through the gas disk, carving paths toward their stars. Others may have been tossed inward violently. The variety of hot Jupiter orbits reflects this diversity. Planets with aligned orbits are likely products of disk migration. Those with dramatic misalignments or retrograde motion hint at dynamical upheaval, gravitational chaos on a massive scale. The theoretical conflicts that once made hot Jupiters seem impossible gradually transformed into a new understanding of planetary evolution. Instead of seeing our solar system as the standard, astronomers began to recognize that planetary systems are dynamic, fluid, and often unruly. Worlds move, orbits shift, systems rearrange themselves. The architecture we observe today is the result of billions of years of gravitational negotiation. Hot Jupiters forced the field to accept this dynamism. Their existence illuminated the limits of the classical formation models and opened the door to a broader view of planet formation, one that acknowledges instability, migration, and the intricate sculpting power of a protoplanetary disk. In the early years of exoplanet discovery, the notion that giant planets could move across their planetary systems seemed almost radical. Orbits were imagined as fixed, sculpted during formation, and left largely unchanged. But the evidence gathered from dozens, then hundreds of exoplanets revealed a universe that behaves far more dynamically. Hot Jupiters, parked perilously close to their stars, provided the clearest sign that many planets do not remain where they are born. Their very existence implies that migration is not an exception, it is a fundamental feature of planetary evolution. Migration unfolds through multiple mechanisms, each driven by distinct physical processes operating at different stages of a planetary system's life. Some pathways are gentle and continuous, others are chaotic, violent, and capable of flinging planets into new configurations that would appear implausible without the mathematics to support them. The earliest mechanism to be understood involves interactions between a planet and the protoplanetary disk that surrounds a young star. This disk, composed of gas and dust, is not static. It flows, swirls, and exerts torques on anything embedded within it. Small and intermediate mass planets experience what is known as Type 1 migration. They do not carve clearings in the disk, but instead generate spiral density waves. One set of waves forms inside their orbit, rotating slightly faster, and another forms outside their orbit, where gas moves more slowly. Each wave exerts a gravitational pull on the planet. In a perfectly symmetric disk, these torques would cancel, but protoplanetary disks are rarely that tidy. Temperature gradients, pressure variations, and density profiles disrupt the balance, allowing one torque to dominate. The outcome is migration. What makes Type 1 migration astonishing is its speed. Under realistic conditions, a planet with only a few Earth masses could drift inward by an astronomical unit in under 1 million years. Compared to the typical disk lifetime of 3 to 10 million years, this process occurs quickly enough that, without some moderating influence, planets should plunge inward regularly. The fact that many planetary systems retain super-Earths and Neptunes at moderate distances suggests that additional physics, disk turbulence, magnetic fields, feedback from planetary heating, intervenes to slow the drift. But for the largest planets, the picture is different. As a growing planet accumulates mass, its gravity becomes strong enough to locally reshape the disk. When the planet reaches roughly Jupiter's mass, it can carve a gap, a region of reduced gas density along its orbit. The planet becomes partially decoupled from the small-scale flow around it, entering the regime known as Type 2 migration. Instead of being pushed by asymmetrical density waves, it becomes embedded in the overall viscous evolution of the disk. Gas continually flows inward toward the star, and the planet migrates with it. Type 2 migration is slower than Type 1, but still efficient enough to carry a giant planet inward by several astronomical units during the disk's lifetime. Both forms of disk migration produce planets with orbits aligned to the stellar equator, the same orientation as the disk. And indeed, many hot Jupiters exhibit such alignment, supporting the idea that they moved inward smoothly while the disk still existed. But not all hot Jupiters obey that pattern. Some trace orbits inclined by dozens of degrees, and others travel retrograde, circling their stars in the opposite direction of stellar rotation. These configurations cannot arise naturally from disk-driven processes. They require disruption, a gravitational shove that transforms a stable orbit into something extreme. This is where dynamical migration comes into focus. High eccentricity migration provides an alternative pathway in which the planet is inserted into a highly elongated orbit rather than drifting steadily inward. Over time, tides raised on the planet and star during close passes drain orbital energy, contracting and circularizing the orbit until the planet settles close to the star. One of the most elegant mechanisms behind such eccentricity pumping is the Kozai-Leadoff effect. It occurs in hierarchical systems where a distant companion, another planet or a stellar partner, revolves in an orbit significantly inclined relative to the inner planet. Although the distant companion is far away, its gravitational influence accumulates over time. The inner planet begins to trade inclination for eccentricity in long, oscillating cycles. Its orbit gradually stretches into a dramatic ellipse, bringing it close to the star on each pass. When the inner planet approaches the star at these near grazing distances, tidal forces become enormous. With each periapsis passage, tides siphon energy from the orbit. Over millions of years, the elongated path shrinks and rounds out, ultimately producing a circular orbit only a few hundredths of an astronomical unit from the star. Another form of disruptive evolution is dynamical scattering. In systems containing multiple giant planets, gravitational interactions can destabilize the architecture once the gas disk dissipates. Without the damping effect of the surrounding gas, the planets interact directly. Close encounters between giants can redistribute angular momentum violently. One planet may be flung outward, while another is thrown inward on a plunging trajectory. If the inward-moving planet ventures close enough, tidal circularization again takes over, trapping it in a hot Jupiter orbit. The process resembles planetary billiards played at astronomical scales, with the stakes measured in millions of kilometers. The evidence for these processes does not rely solely on theory. Simulations carried out since the early 2000s have shown that both gentle disk migration and chaotic dynamical migration can reproduce the observed population of hot Jupiters. Monte Carlo studies comparing synthetic planetary systems with real exoplanet catalogues reveal that no single mechanism can explain all hot Jupiters. Instead, the population appears to be a blend. Well-aligned systems point toward disk migration. Misaligned or retrograde planets reflect the fingerprints of dynamical upheavals, either Kozai-Leadoff interactions or scattering. Observationally, many hot Jupiter systems include distant massive companions that could serve as drivers of eccentricity oscillations. Others show no such companions, aligning more comfortably with smooth disk migration. And then, there are the planets whose orbits show signs of decay, tiny deviations in transit timing that may indicate they arrived in their current positions relatively recently. These cases suggest that some hot Jupiters might still be spiraling slowly inward under the influence of tidal friction, Together, migration mechanisms reveal a universe where planets are not fixed ornaments, but mobile participants in a dynamic system. They can drift, scatter, flip, plunge, and circularize. Their paths are shaped by gas, gravity, and time. Hot Jupiters represent the final outcome of these long migrations, worlds that travelled across astronomical units to reach orbits measured in million-kilometre intervals, transformed by every stage of the journey. The atmosphere of a hot Jupiter does not behave like the atmosphere of any planet in the solar system. At the temperatures these worlds endure, chemistry enters regimes that push beyond familiar intuition. Molecules fall apart under the weight of thermal energy. Atoms become ionized, metals evaporate. Materials that would condense into solids in colder environments remain suspended as vapor. These planets are not simply hot. Their atmospheres operate in a thermochemical landscape closer to that found inside industrial furnaces or stellar envelopes than within any planetary environment Earth has ever experienced. The heat begins with proximity. A typical hot Jupiter orbits so close to its star that the incoming flux at the top of its atmosphere can be thousands of times stronger than what Jupiter receives from the Sun. In the most extreme cases, ultra-hot Jupiters, the dayside temperature exceeds 2,000 degrees Celsius, about 3,600 degrees Fahrenheit. Some reach or surpass 3,000 degrees Celsius, around 5,400 degrees Fahrenheit, entering a regime where common molecules begin to dissociate. Water vapor, normally a stable atmospheric constituent, breaks into hydrogen and oxygen atoms. Methane transforms into carbon monoxide or dissociates further under the intense ultraviolet radiation pouring from the star. Even nitrogen, one of the most robust molecules in planetary atmospheres, struggles to remain intact. These temperatures introduce physics more commonly studied in laboratory plasmas than in planetary science. Once molecules dissociate, collisions among the resulting atoms may strip electrons away, producing partially ionized gas. Ionization becomes significant in ultra-hot Jupiters, where the dayside atmosphere contains free electrons capable of interacting with magnetic fields and influencing heat transport. This partially ionized region absorbs stellar radiation in complex ways, reshaping the vertical temperature structure. The temperature gradient of a planet's atmosphere typically decreases with altitude. On Earth and Jupiter, higher atmospheric layers are cooler until reaching specific boundaries, such as the thermosphere. For many hot Jupiters, however, the opposite occurs. Their upper atmospheres heat dramatically, producing temperature inversions, regions where temperature increases with height. Early observations from the Spitzer Space Telescope in the mid-2000s suggested such inversions might be common. Certain hot Jupiters exhibited emission features in their spectra rather than the expected absorption signatures. In atmospheric chemistry, this is the calling card of an inverted temperature structure. Initially, researchers suspected molecules such as titanium oxide, TiO, or vanadium oxide, VO, might be responsible. These compounds are strong absorbers of visible and ultraviolet light and could, in principle, heat the upper atmosphere enough to create an inversion. Models predicted that planets hot enough to keep TiO and VO in gaseous form should produce inverted temperature profiles, while cooler planets would not. This framework provided a neat division between PM-class and PL-class hot Jupiters, an analogy to the classification of brown dwarfs. But over time, the data grew more complicated. Not all hot Jupiters displayed inversions, even at temperatures where TiO and VO should remain gaseous. Others showed evidence of inversion-like behavior without strong signatures of these molecules. Additional explanations emerged. Silicate clouds might trap heat. Absorption by atomic metals, iron, magnesium, or calcium, could contribute. In some cases, even ionized hydrogen may play a role. The physics of these atmospheres proved too complex to fit within a simple two-class model. As telescopes improved, so did the clarity of the chemical picture. Observations from the Hubble Space Telescope revealed unmistakable signatures of sodium and potassium. alkali metals with strong resonance lines in the optical spectrum. These elements survive in gas, form only at high temperatures, marking hot Jupiters as worlds with atmospheres heated well beyond terrestrial norms. Hubble also detected water vapor, though not always in expected quantities. In some planets, clouds or haze layers obscure the deep atmosphere, flattening spectral signatures. In others, the water may be partially dissociated, altering the spectral profile. The Spitzer telescope, operating in the infrared, provided crucial measurements of dayside brightness temperatures. Some planets glow at temperatures hotter than many stars' photospheres. Others show surprisingly efficient heat redistribution, with the night side remaining warm despite perpetual darkness. The balance between day-night heat flow hinges on atmospheric dynamics. At high temperatures, the mean molecular weight of the atmosphere decreases, increasing the scale height and altering wind speeds. Ionization also introduces magnetic drag, which may suppress winds on the hottest planets, allowing the day side to heat even more intensely. A dramatic example is WASP 121b, an ultra-hot Jupiter studied extensively with Hubble and Spitzer. Its atmosphere reaches temperatures around 2,700 degrees Celsius, nearly 5,000 degrees Fahrenheit on the day side, hot enough for metal-bearing molecules to break apart. Observations revealed the presence of iron and magnesium ions, evidence of an atmosphere undergoing continuous photochemical and thermal processing. The planet's temperature profile displays a pronounced inversion, consistent with absorption by metal ions rather than TiO or VO. Night-side temperatures remain far lower, yet still above 1,000 degrees Celsius, about 1,800 degrees Fahrenheit, insufficient for molecules such as water to fully reform. Even on the dark hemisphere, the chemistry never escapes the influence of extreme heat. The James Webb Space Telescope pushed this field into an even more detailed regime. With its broad wavelength coverage and high sensitivity, jwst can detect subtle spectral features unachievable with previous instruments. Observations of planets like WASP 39b and WASP 18b have revealed fine-resolution molecular signatures, confirming the presence of carbon dioxide, sulfur compounds, metal hydrides, and atomic species. In particular, the detection of sulfur dioxide, SO2, in WASP 39b's atmosphere surprised researchers. Its presence implies active photochemistry driven by stellar ultraviolet radiation, a sophisticated chemical network reminiscent of reactions occurring in Venus's upper atmosphere, but at far higher temperatures. Another striking case is WASP 18b, an ultra-hot Jupiter with day-side temperatures exceeding 2,800 degrees Celsius, around 5,100 degrees Fahrenheit. jwst observations revealed that the planet's atmosphere lacks water on the day side, not because water never formed, but because it is thermally dissociated. Instead, the spectrum showed signatures of ionized metals and potential hints of H- opacity, a continuum opacity source arising from negatively charged hydrogen ions. This type of opacity dominates in stellar atmospheres, making WASP 18b's dayside resemble the outer layers of a star more than a planetary environment. Such findings underscore that ultra-hot Jupiters operate at the boundary between planetary physics and stellar physics. Temperature inversions continue to provide one of the most intriguing puzzles. Some planets exhibit strong inversions, others almost none. The presence or absence of TiO or VO does not fully account for the differences. Instead, metallicity, vertical mixing, photochemical destruction, and cloud opacity all appear to shape the temperature profile. High-altitude hazes can absorb radiation, acting as heaters. In other planets, reflective clouds may shield deep layers from stellar energy, suppressing the formation of inversions. No single model captures the diversity. Each planet reflects a unique balance of chemistry, irradiation, and atmospheric circulation. Beyond the chemistry, the structural consequences of extreme heating are profound. As the upper atmosphere expands, the planet becomes more vulnerable to atmospheric escape. Hydrogen atoms propelled by high temperatures and ultraviolet irradiation may stream outward, forming extended envelopes detectable through absorption in the Lyman alpha line. In the most extreme examples, the atmosphere escapes in comet-like tails stretching behind the planet. This process contributes to long-term mass loss, which in turn feeds back into the temperature-pressure profile of the surviving atmosphere. The interplay of thermal dissociation, ionization, and chemistry transforms these atmospheres into experimental arenas. They allow researchers to probe reactions that occur at high temperatures, study the transition from molecular to atomic gas, and explore ionization regimes rarely encountered in planetary science. They also reveal how stars influence their planets, not just through gravity, but through radiative and chemical forcing that reshapes the fundamental properties of the atmosphere. Hot Jupiters began as a surprise. Today they are among the best characterized exoplanets in existence, thanks largely to their extreme environments. Their atmospheres contain signatures of heat so severe that matter behaves differently, sometimes like a gas, sometimes like a plasma, sometimes like something in between. They stand at the intersection of planetary science, stellar physics, and atmospheric chemistry, expanding our understanding of what a planet can be under the most intense conditions a star can impose. If you could hover high above the atmosphere of a hot Jupiter, the first thing you would notice is movement. Constant, ceaseless, planet-spanning movement. The entire atmosphere behaves like a global conveyor of heat, pushed and pulled by pressure gradients far stronger than anything Earth ever experiences. On our own planet, wind speeds can reach a few hundred kilometers per hour during extreme storms, about 120 miles per hour. On a hot Jupiter, winds routinely exceed several kilometers per second, more than 5,000 miles per hour, fast enough to cross an Earth-sized world in under an hour. In these environments, wind is not just a feature of the weather, it is the weather. The fundamental driver is temperature contrast. Because most hot Jupiters are tidally locked, they present the same hemisphere to their star at all times. One side is exposed to continuous, unrelenting radiation. The other side exists in perpetual darkness. The day side can reach temperatures above 2,000 degrees Celsius, around 3,600 degrees Fahrenheit, hot enough to vaporize metals. The night side, while cooler, may still remain above 1,000 degrees Celsius, roughly 1,800 degrees Fahrenheit. This enormous thermal contrast, on the order of 1,000 degrees or more, creates pressure gradients of staggering magnitude. Hot gas expands, lowering density. Cooler gas contracts. The atmosphere attempts to redistribute this imbalance through winds that flow endlessly from day to night. Yet the movement is not a simple radial flow. The rotation of the planet, even in a tidally locked state, generates a Coriolis effect. Combined with strong vertical and horizontal temperature gradients, this leads to the formation of powerful jet streams. The dominant feature is usually an eastward equatorial jet. Models suggest that this jet can wrap completely around the planet, circling it in a smooth, continuous current. On many hot Jupiters, the equatorial jet pushes the hottest region eastward from the substellar point, the point directly beneath the star, creating a thermal hotspot shift detectable in infrared observations. Telescopes such as Spitzer have been able to map these temperature distributions by monitoring changes in brightness as the planet orbits its star. For some worlds, the hotspot is shifted by tens of degrees in longitude, evidence of fast-moving winds advecting heat before it is radiated away. On others, especially the hottest planets, the winds appear less efficient. Ionization in the upper atmosphere introduces magnetic drag, slowing the flow and allowing the day side to heat even more intensely, producing sharper contrasts between the hemispheres. Vertical circulation adds another layer of complexity. Heated gas near the substellar point rises, cools as it expands, and sinks elsewhere. Meanwhile, cooler gas from the night side flows back toward the day side at deeper layers, creating a three-dimensional circulation pattern. General circulation models, numerical simulations adapted from atmospheric science on Earth, predict giant overturning cells spanning the entire planet. These simulations have become essential tools for understanding the thermal structure of hot Jupiters, helping researchers interpret observations from Hubble, Spitzer, and now jwst. One of the most striking consequences of these circulation patterns is what happens to the chemistry of the atmosphere. On the scorching day side, molecules such as water, titanium oxide, or iron-bearing compounds may dissociate or exist as high-temperature gases. When winds carry these gases toward the night side, they encounter lower temperatures. Suddenly, the atmosphere becomes capable of condensation, not of water or methane, as on Earth or Jupiter, but of materials far more exotic. Iron, for example, may condense on the night side of the hottest Jupiters. Observations of the planet known as WASP 76b provided a striking hint of this process. Spectra collected during transit showed gaseous iron on the evening terminator, the boundary where the day side transitions to night, but the same signature was absent on the morning terminator. The interpretation is that iron vapor is carried from the hot day side into cooler night side regions, where it condenses, possibly falling as droplets of molten metal. The image of iron rain may sound like science fiction, but the chemistry and thermodynamics support it. When the temperature drops below the condensation point, metallic vapor becomes liquid. Other condensates are equally unusual. Corundum, a crystalline form of aluminum oxide, can condense on the night side of some hot Jupiters. If that material rings a bell, it's because corundum is what forms rubies and sapphires on Earth. In a hot Jupiter atmosphere, these crystals could potentially appear as particulate clouds, carried aloft by winds before evaporating again on the day side. Titanium-bearing compounds may follow similar condensation cycles. The phrase exotic weather hardly captures the strangeness of these environments. Clouds of vaporized rock on the day side, mineral condensation on the night side, and complete evaporation at sunrise. For planets with slightly lower temperatures, silicate clouds may form. These clouds, composed of tiny glass-like grains, could scatter light efficiently and flatten spectral features, making the atmosphere more opaque in observations. Some hot Jupiters display muted water absorption lines, implying cloud layers that obscure deeper atmospheric regions. High-altitude clouds on these worlds are not thin wisps, but global structures shaped by the immense dynamics of circulation. The challenge in interpreting these phenomena lies in the interconnectedness of the system. The wind patterns influence condensation. Condensation affects opacity. Opacity determines how deep observations can probe, and temperature distributions feed back into wind speeds. General circulation models attempt to capture all of this, solving equations that describe fluid dynamics, radiative transfer, and thermochemistry simultaneously. But even the best models struggle with uncertainties. The behavior of high-temperature gases, the role of magnetic fields in partially ionized atmospheres, the microphysics of exotic condensates, these details are still being refined. One telling insight from circulation studies is how the efficiency of heat redistribution changes with temperature. For moderately hot Jupiters, winds can transport heat effectively, reducing the day-night temperature contrast. But as temperatures climb into the realm of ultra-hot Jupiters, the chemistry changes. Molecules dissociate. Ionization increases. The atmosphere becomes thinner in terms of molecular weight, but more influenced by magnetic effects. As a result, winds slow. The day side becomes hotter, the night side cooler. The thermal contrast sharpens. Heat redistribution becomes less efficient. Observations confirm this trend. The hottest planets exhibit the largest differences between their hemispheres. The existence of eastward jet streams provides another clue to the underlying physics. In a tidally locked configuration, the stellar heating pattern is fixed relative to the planet's surface. This creates a stationary wave pattern in the atmosphere, longitudinal waves that interact with rotation to produce a super-rotating jet. The jet is not a natural feature of a rotating planet. It is an emergent consequence of intense, localized heating. Even small variations in wind speed or temperature can shift the jet's structure, altering the location of the hotspot. These wind systems operate at scales far beyond terrestrial experience. The entire planet becomes a single integrated circulation machine. Heating, cooling, chemical reactions, and fluid dynamics combine into a cohesive, global pattern. And through observations, researchers can observe this pattern indirectly, mapping brightness variations, identifying phase shifts, and detecting chemical species at different locations around the orbit. In the end, the winds of a hot Jupiter are not merely chaotic storms, they are the planet's response to living in an environment defined by extremes. They redistribute heat, sculpt clouds, govern chemistry, and shape the very structure of the atmosphere. They turn the planet into a world of continuous motion, one where night and day are not simple divisions of sunlight, but engines that drive a planetary system infinitely more dynamic than anything we have ever known. When a planet orbits close enough to its star, the boundary between atmosphere and space becomes blurred. Under extreme irradiation, the upper layers heat, expand, and eventually begin to escape the planet's gravitational pull. On Earth, atmospheric escape is a subtle process. Hydrogen leaks away slowly, oxygen gradually recombines, and the exosphere remains thin and cold. For a hot Jupiter, the story is entirely different. The heat is so intense that the upper atmosphere swells outward, forming a vast extended envelope of gas. At these distances, sunlight is not gentle illumination, but a driving force that reshapes the very structure of the planet. The mechanism behind this phenomenon is known as hydrodynamic escape. Unlike the quiet, particle-by-particle loss Earth experiences, hydrodynamic escape behaves more like a fluid flow. As stellar ultraviolet radiation heats the upper atmosphere, gas expands rapidly. Pressure builds. The atmosphere begins to accelerate outward in a continuous stream, similar to a solar wind flowing from a star. If the heating is strong enough, the flow reaches escape velocity, allowing large quantities of gas, primarily hydrogen, to leave the planet entirely. This process was once theoretical. Then, in 2003, a landmark detection confirmed it in dramatic detail. Astronomers studying the planet HD 209458b with the Hubble Space Telescope observed that the planet's transit was deeper in ultraviolet wavelengths than in visible light. The explanation was extraordinary. The planet was surrounded by a cloud of hydrogen so large that it extended tens of thousands of kilometers beyond the planet's radius. Further modelling indicated that the hydrogen was not simply a static cloud, but a stream of escaping gas forming a long tail-like structure trailing the planet, similar to a comet, but driven by stellar radiation rather than sublimating ice. HD 209458b became one of the most iconic exoplanets for this reason. It provided direct evidence that some hot Jupiters are actively losing mass. The rates vary, but estimates suggest that planets like this may lose between 10 to the power of 8 and 10 to the power of 10 grams of material per second. Spread across billions of years, such loss can significantly alter the structure of the planet, especially if it begins with a relatively small mass. The most extreme cases may lose their entire gaseous envelopes, leaving behind a stripped core, a rocky or metallic remnant that no longer resembles a gas giant at all. This possibility has led scientists to wonder whether some close-in super-Earths or mini-Neptunes might in fact be the skeletal remains of once massive planets. Other planets have shown similar signatures. HD 189733b displays evidence of atmospheric escape through enhanced absorption in the Lyman alpha line. Observations even suggest the presence of silicon and magnesium ions in the outflow, implying that heavy elements are being carried along with the escaping hydrogen. These detections point to a more complex escape environment than originally expected, one shaped not only by heat but also by wind interactions and magnetic forces. Magnetic fields play a subtle but important role. A hot Jupiter with a magnetic field will shape its escaping atmosphere into structured flows. The interaction between stellar wind and planetary magnetic field can compress the exosphere, induce magnetotails, or even funnel particles along magnetic field lines. In some systems, the escaping atmosphere may shock against the incoming stellar wind, creating a bow shock ahead of the planet, much like the one Earth forms in front of its magnetosphere. Some hot Jupiters appear to spiral slightly inward over time, their orbits decaying due to tidal dissipation within the star. If the orbit shifts gradually closer, the atmospheric escape rate may accelerate. As the star ages and increases in luminosity, its ultraviolet flux grows, again increasing escape. The evolution of a hot Jupiter thus becomes a complex interplay of orbital decay, stellar activity, and atmospheric loss, an extended interaction that lasts billions of years. One of the most intriguing aspects of atmospheric escape involves the transition between the molecular and atomic layers. In ultra-hot Jupiters, molecules are largely dissociated on the day side, leaving a mix of atoms and ions in the upper atmosphere. These atoms can be accelerated outward more efficiently because they experience less radiative cooling. The presence of ionized metals, detected in planets such as WASP-121b and WASP-18b, implies that the upper atmosphere functions partly like a stellar chromosphere, a region where strong heating and ionization coexist with dynamic flows. In some planets, hydrogen escape may be so vigorous that it entrains heavier atoms, dragging them upward in a hydrodynamic wind. This process, known as drag-limited escape, suggests that once escape begins, it can reshape the vertical structure of the atmosphere and alter its chemical inventory. Over time, this could change the observable spectrum, making the planet appear depleted in certain species that are easily swept away. Magnetic interactions offer another layer of complexity. For planets orbiting active stars, charged particles from the stellar wind may bombard the upper atmosphere, heating it further or driving additional escape. In extreme cases, reconnection events between stellar and planetary magnetic fields may inject bursts of energy into the exosphere, briefly enhancing outflow rates. These interactions are difficult to observe directly, but signatures may appear in transit timing variations, asymmetries in ultraviolet absorption, or periodic modulations associated with the planet's magnetic geometry. Some models predict that atmospheric escape can lead to measurable changes in the planet's mass over the lifetime of the system. A hot Jupiter with a mass near that of Saturn, for example, could theoretically lose several % of its mass across billions of years. A smaller Neptune-sized planet might lose an even larger fraction, potentially leaving behind a rocky super-Earth. This process, when operating across large populations of planets, could explain why close-in Neptune-sized worlds are relatively rare, a feature known as the hot Neptune desert. Escape, then, is not merely an edge phenomenon. It is a transformative process that shapes the long-term evolution of close-in planets. It determines what remains after billions of years of irradiation, how orbits shift over time, and how energy from a star sculpts the atmospheres around it. The sight of a hydrogen tail stretching behind a distant world is not just a snapshot of atmospheric loss, it is evidence of a planet slowly changing form, shaped continuously by its star. Hot Jupiters endure heat that gas giants were never meant to experience. Their atmospheres expand, accelerate, and escape, creating structures that bridge the boundary between planet and space environment. Through them, astronomers observe not just weather or chemistry, but planetary evolution in action. On a hot Jupiter, the concept of day and night becomes something permanent, structural, and unchanging. Because these planets orbit their stars at such close distances, tidal forces act relentlessly to slow their rotation until the same hemisphere always faces the star. The outcome is tidal locking, a state where the planet's rotation period matches its orbital period. Unlike Earth, where sunrise and sunset sweep across the surface in a continuous cycle, a tidally locked world has a hemisphere of perpetual daylight and another of eternal darkness. Tidal locking is not just a geometric feature, it reflects the enormous gravitational torque the star exerts on the planet. At distances of only a few million kilometers, the differential gravitational pull between the near and far sides of the planet is immense. This imbalance stretches the planet slightly into an elongated shape. As the planet rotates, the star tries to realign this bulge. The friction generated by repeatedly pulling the bulge into alignment drains rotational energy from the planet, slowing the spin until the struggle ends in equilibrium. But even after synchronization, tidal forces continue to act. If the planet's orbit is even slightly eccentric, the gravitational pull varies during each revolution, periodically flexing the planet's interior. This cyclic flexing dissipates energy as heat, reminiscent of the process that powers volcanic activity on Jupiter's moon, Io, but on a far larger scale. For some hot Jupiters, tidal heating may alter internal structure, influence atmospheric dynamics, or indirectly affect inflation, contributing to the puzzlingly large radii observed in many of these planets. The star does not remain untouched in this exchange. Tidal interactions transfer angular momentum between planet and star, allowing the orbit to evolve over time. If the star rotates more slowly than the planet orbits, as is common for Sun-like stars, the planet gradually loses orbital energy and spirals inward. This process, known as orbital decay, proceeds slowly but inexorably. Measurements of certain systems, such as WASP-12b, suggest decay rates large enough to detect within a human lifetime. Observations indicate the orbit may be shrinking by a few milliseconds per year, tiny in absolute terms but profound on astronomical timescales. If sustained, this decay will eventually deliver the planet into the star's outer layers. The possibility that a planet might one day be engulfed is not hypothetical. Stellar evolution models predict that as stars age, especially when they enter the red giant phase, their outer layers expand dramatically. A hot Jupiter that orbits safely during the star's main sequence lifetime may find itself inside the star's atmosphere hundreds of millions of years later. The moment of engulfment would be brief and violent. The planet would spiral inward due to drag in the stellar envelope, depositing angular momentum and heat. In some cases, this could alter the star's rotation or trigger enhanced activity. Evidence for such past interactions may linger in stellar chemistry, unusual abundance patterns hinting that a star once consumed a planet. Before engulfment, the interactions between star and planet can take subtler forms. Magnetic fields, for instance, link the two bodies through charged particles and energetic currents. A planet orbiting close to a magnetically active star moves through the star's extended magnetosphere. If the planet possesses its own magnetic field, the interaction can resemble the coupling between Jupiter and its moon Io, where electric currents flow along magnetic field lines. For hot Jupiters, such interactions could produce observable signatures, localized heating in the stellar atmosphere, synchronous modulations in stellar emission, or even faint radio signals associated with cyclotron radiation. The search for star-planet magnetic interactions has intensified in recent years. Observations of certain systems have revealed periodic enhancements in stellar activity that match the orbital period of the planet rather than the star's rotation. This suggests that the planet may be triggering or amplifying magnetic reconnection events on the star. While the evidence is still being refined, the emerging picture hints at a relationship where close-in planets act almost like conductors moving through a magnetic field, generating currents and sparks of energy. Star-planet interactions extend even further. The upper atmospheres of hot Jupiters often contain ionized gas. When this ionized material moves through the stellar magnetic field, it can induce electric currents. These currents dissipate energy, potentially heating the atmosphere or influencing wind patterns. In extreme cases, the interaction may compress the planetary magnetosphere, exposing more of the atmosphere to erosion by stellar wind and accelerating atmospheric escape. Some systems hint at bow shocks, regions where the stellar wind slams into the planet's magnetic field, heating the gas ahead of the planet. These structures might shift the apparent timing of transits in ultraviolet wavelengths as the bow shock absorbs light before the planet itself begins to cross the stellar disk. The detection of such asymmetries provides indirect evidence for intense magnetic interactions that operate in the space between star and planet. Behind all these phenomena is the remarkable gravitational partnership formed by proximity. A hot Jupiter is not just orbiting its star, it is deeply entangled with it. The star's gravity shapes the planet's rotation, heating its interior, expanding its atmosphere, and gradually pulling it inward. The planet, in turn, exerts subtle influences on the star, tidal distortions, magnetic feedback, perhaps even chemical enrichment if engulfment occurs. As the star ages, the balance becomes increasingly unstable. A star entering its subgiant or red giant phase expands outward. Orbits that were once safe become perilous. The threshold distance for engulfment widens, and planets that had survived for billions of years find themselves drifting toward destruction. The final spiral occurs rapidly, probably in a matter of years or decades once the planet enters the star's envelope. Clues to this fate exist in the astrophysical record. Some red giants spin faster than they should, given their age and angular momentum loss. Some show unexpected lithium abundances, an element easily destroyed in stellar interiors but replenished if a planet is consumed. These anomalies may represent the remnants of past star-planet interactions, silent evidence that planets do not always survive the changing lives of their stars. Hot Jupiters live on a precarious edge. They exist in a gravitational and magnetic environment so intense that their atmospheres, interiors, and orbits are all sculpted by the star. Their eventual fate is almost always the same: decay, engulfment, and dissolution. But the journey to that end reveals a complex interplay of forces: tides, magnetic fields, winds, and radiation that shape the evolution of both planet and star. Some hot Jupiters orbit close, and some orbit astonishingly close. A small but remarkable subset completes a full revolution around its star in less than a single Earth day. These ultra-short-period giants sweep across orbits so tight that the star dominates nearly every aspect of their behavior: temperature, shape, atmosphere, even motion through space. Yet for astronomers, these planets are more than curiosities. They are tools, instruments, probes carved by nature and placed in extreme environments where they can reveal properties of their stars that would otherwise remain hidden. A planet in a sub-day orbit lies only a few stellar radii from the photosphere. At distances this small, gravitational tides, magnetic stresses, and stellar winds exert overwhelming influence. The planet, in turn, responds measurably to these forces, allowing astronomers to infer star-planet interactions with a level of precision impossible in wider systems. In many ways, the planet becomes a tracer, a detectable object whose behavior encodes information about the star's internal structure and its surrounding environment. The orbital timescales alone reshape expectations. Earth takes a year to circle the Sun. Mercury, the fastest planet in our solar system, completes its orbit in 88 days. But planets such as WASP 103b or NGTS 10b finish the cycle in under 24 hours. At such speed, the star's gravitational field is not just a background force, but a sculpting influence. The planet's shape becomes distorted, stretched slightly along the star-facing axis. Tidal forces pull on the gas giant continuously, amplifying the natural tidal bulge and affecting internal circulation. Even subtle changes in the star's gravity field, arising from internal density structure, rotation, or oblateness, leave fingerprints in the planet's orbit. One of the earliest insights came from measuring slight deviations in transit timing. When a planet crosses the face of its star, the timing of that event can be measured with remarkable accuracy. If the orbit is perfectly stable and periodic, transits occur like clockwork. But for ultra-short period planets, gravitational tides raised on the star extract orbital energy from the planet over time. The orbit gradually shrinks, and each transit occurs just a little earlier than expected. These deviations are known as transit timing variations, or TTVS. Detecting orbital decay in real time is challenging. The shift in timing can be only a few milliseconds each year. Yet planets such as WASP-12b have shown evidence that their orbital periods are decreasing measurably, suggesting rapid tidal dissipation inside the star. The rate of decay reveals something fundamental: how efficiently the star absorbs tidal energy. This efficiency depends on the star's internal structure, how energy propagates through its convective zone, how waves dissipate in its radiative interior, and how angular momentum is transferred between the orbit and stellar rotation. In this sense, an ultra-short period hot Jupiter becomes a diagnostic tool for stellar astrophysics, offering insights into processes usually hidden from view. Another powerful application involves stellar winds. A star emits a continuous flow of charged particles that stream outward into space. Closer to the star, the wind density and velocity rise sharply. An ultra-short period planet plows directly through this environment. As it does, its atmosphere and magnetic field interact with the wind in distinctive ways. These interactions can create bow shocks, stripped material, and heated gas layers, all of which leave spectroscopic signatures during transit. When astronomers detect asymmetries in ultraviolet absorption or extended tails of escaping gas pointing away from the star, they can infer parameters of the stellar wind, its density, temperature, and velocity at distances far too close for any spacecraft to probe. Winds also contribute to atmospheric escape. In a sub-day orbit, the intensity of ultraviolet irradiation is extreme. Hydrogen in the upper atmosphere absorbs this energy and begins to escape hydrodynamically. The stellar wind then pushes on this outflow, shaping it into a tail or stream. By observing how the tail responds to changes in stellar activity, such as flares or magnetic cycles, astronomers can deduce real-time variations in the wind, much like watching the movement of smoke in a breeze reveals the presence of air currents. These planets also help constrain magnetic fields. For a magnetic hot Jupiter, interactions with the stellar wind can generate radio emissions through cyclotron processes. Although such signals remain elusive, upcoming observations with sensitive radio arrays may detect them. If successful, they would provide direct measurements of planetary magnetic fields, measurements that currently elude even the best theoretical models. Understanding magnetic fields is crucial because they influence atmospheric escape rates, interior structure, and even the long-term survival of close-in planets. Ultra-short-period hot Jupiters also offer insight into the tidal quality factor of stars, a parameter that describes how efficiently a star converts tidal energy into heat. This factor is notoriously difficult to calculate, as it depends on complex physical processes such as wave dissipation, internal mixing, and magnetic coupling. But when a planet spirals inward, the rate of orbital decay encodes this parameter. With enough transit timing measurements, astronomers can constrain the tidal quality factor directly, allowing them to better understand the internal physics of stars at different evolutionary stages. Another surprising diagnostic involves stellar oblateness. Rapidly rotating stars bulge at the equator and flatten at the poles. If a planet orbits extremely close, the star's uneven gravitational field can influence the orbit, altering precession rates. By tracking the orientation and timing of transits, astronomers can measure changes in orbital alignment and infer how much the star's rotation deviates from spherical symmetry. This offers rare observational access to stellar rotation profiles and angular momentum distribution. These planets even help probe stellar activity cycles. In some systems, the depth and shape of transits vary with time, modulated by star spots on the stellar surface. Because ultra-short period planets orbit so frequently, they sample different longitudes of the star at a high cadence. This effectively turns the planet into a scanning instrument that maps star spot distribution, stellar rotation, and magnetic cycles. It is a method no spacecraft could accomplish, a natural satellite orbiting the star with unwavering precision, measuring changes in brightness and activity in real time. The final layer of insight involves the long-term destiny of these planets. Many ultra-short period hot Jupiters orbit so close that their Roche lobes, the gravitational boundaries that define where material remains bound to the planet, begin to shrink. If a planet expands slightly due to heating or tidal inflation, material may spill over toward the star. This mass transfer could create an observable accretion stream. Although direct evidence remains limited, hints appear in certain ultraviolet observations and in the anomalously high activity levels of some host stars. These cases raise a deeper question. How many hot Jupiters have already been engulfed, and what chemical or dynamical signatures might remain in the stars that consumed them? In the end, ultra-short period hot Jupiters function as natural laboratories. Their extreme environments amplify subtle interactions, gravitational, magnetic, radiative, and tidal, turning them into probes of stellar interiors and stellar winds. Their orbits drift, their atmospheres respond, their shapes and temperatures shift in ways that trace the physics of the stars they orbit. They are not merely planets surviving in unfathomable proximity. They are instruments written into the fabric of astrophysics, revealing the hidden mechanics of stars by enduring their fullest intensity. No two hot Jupiters are truly alike, even though they share a basic definition. Gas giants orbiting extraordinarily close to their stars. Their physical properties vary so widely that the category contains some of the most puzzling planets ever discovered. For every typical hot Jupiter, there is another whose radius is inexplicably swollen, or one that is compact and dense, or another whose orbit is flipped almost backward. Each anomaly reveals something about the physics shaping these worlds, and together they show how diverse planetary systems can be. One of the earliest surprises was the discovery of inflated hot Jupiters, planets whose sizes far exceed what their masses should allow. A gas giant with the mass of Jupiter should have a radius close to Jupiter's. Yet many hot Jupiters are 20, 30, or even 80% larger than expected. Some reach radii of 1.8 times Jupiter's size. These swollen planets have densities lower than cork or balsa wood, raising the question, what mechanism could pump so much heat into the interior that the planet expands against gravity? Multiple theories have emerged over the years. One idea involves ohmic heating. In ultra-hot atmospheres, ionized particles move through the planet's magnetic field, generating electric currents that then dissipate as heat deep within the envelope. Another possibility is tidal heating. If the orbit is slightly eccentric, even by a tiny amount, tidal flexing could warm the interior. A third explanation involves the absorption of stellar radiation high in the atmosphere by molecules or hazes that transport energy downward inefficiently, causing heat to build up. None of these mechanisms alone fully explains all inflated planets, suggesting that several may operate simultaneously depending on the specific environment. Just as perplexing are the denser-than-expected hot Jupiters. Some appear compact, even compressed, with radii smaller than Jupiter's despite greater mass. A few approach densities similar to that of steel. These planets challenge assumptions about internal structure and composition. A gas giant should become more compressible under gravity as mass increases, causing the radius to plateau. But the densest hot Jupiters deviate from theoretical curves, implying unusual internal makeups. Some may contain massive heavy element cores, 50, 100, or even 150 Earth masses of metal and rock buried beneath their gaseous envelopes. Others may be compacted by extreme irradiation that removes outer atmospheric layers over time, leaving a smaller, more gravitationally bound world behind. The diversity in density suggests that planet formation is far more variable than the neat diagrams found in textbooks. The starting ingredients of a planet and the environment in which it forms can imprint themselves into its structure long after migration brings the planet inward. Orbital alignment provides another layer of complexity. Early models assumed that planets should orbit in the same plane as their star's equator, aligned with the rotation of the protoplanetary disk in which they formed. For the first few hot Jupiters, this seemed to hold true. Then came evidence of misalignment. Many hot Jupiters orbit their stars at steep angles. Some travel perpendicular to the star's rotation axis. Others orbit in retrograde, moving opposite the star's rotation. These discoveries were made possible by the Rossiter-McLaughlin effect, a subtle distortion of stellar spectral lines during a planetary transit. As the planet blocks different regions of the star's rotating surface, it temporarily changes the observed Doppler shift. If the planet crosses the star's equator in the same direction the star rotates, the distortion follows a predictable pattern. If the planet's orbit is tilted or reversed, the distortion changes accordingly. Measuring this effect has revealed orbital geometries that defy the once common assumption of orderly alignment. The existence of misaligned and retrograde hot Jupiters strongly supports migration pathways involving dynamical interactions rather than smooth disk migration. A violent encounter with another planet or the gravitational influence of a distant companion can tilt the orbit dramatically. Over time, tides circularize the orbit, yet preserve the inclination, leaving behind a stable hot Jupiter with a memory of its chaotic past etched into its orbital geometry. A separate class of puzzles emerges from systems that host hot Jupiters alongside additional planets. For years, the prevailing belief was that hot Jupiters tended to form in isolation, their migrations so disruptive that other planets were either ejected or prevented from forming. But discoveries from missions like Kepler began identifying systems where hot Jupiters coexist with smaller inner planets or distant massive companions. These configurations challenge the assumptions about how migration should affect planetary architecture. In some systems, the hot Jupiter occupies a compact, stable orbit, while super-Earths or mini-Neptunes circle farther out, an arrangement that seems dynamically delicate. In others, long-period gas giants share the system, hinting that multiple giant planets survived the migration process. The architecture of these systems forces models to incorporate more nuanced migration histories. Instead of a single inward spiral, the hot Jupiter may have moved early in disk evolution, leaving time for smaller planets to form afterward. Or the migration may have been halted by resonant interactions with other planets or with the inner edge of the disk. Then there are the rare examples of hot Jupiters in multi-resonant systems, where orbital periods show simple numerical ratios, evidence that the planets once interacted strongly. Such resonances require fine timing and precise gravitational exchanges during formation or migration. They demonstrate that some hot Jupiters moved inward through a more orderly process than others, guided by resonant locks rather than violent scattering. These systems underscore the diversity of outcomes planetary formation can produce. Some hot Jupiters stand alone, survivors of catastrophic rearrangement. Others reside in systems that appear remarkably peaceful. The differences reveal that planetary evolution is not governed by a single pathway, but by a spectrum of interacting processes: disk physics, gravitational dynamics, atmospheric loss, and stellar evolution, all working simultaneously. Even the stars that host these planets vary widely. Hot Jupiters around cooler stars often show more aligned orbits, perhaps because tidal forces more effectively realign the system. Those around hotter, more massive stars display greater misalignment, supporting the idea that tides operate differently depending on stellar structure. This stellar diversity adds another layer to interpreting planetary diversity, making each system a case study in coupled evolution between star and planet. What emerges from all these observations is a portrait of hot Jupiters, not as a uniform class, but as an umbrella category spanning extremes of physics. Swollen giants glowing with internal heat, dense worlds compacted under immense gravity, planets tilted at improbable angles, systems with companions that should not have survived. Each outlier adds a new piece to the puzzle, revealing a universe where planetary systems do not settle into one predictable shape, but grow into forms shaped by chance, conflict, and the underlying fabric of their environments. Hot Jupiters were once a surprise. Now they are a laboratory for diversity, an invitation to explore how many ways a planet can exist close to its star. As the study of hot Jupiters moves into its next era, the questions become more intricate, the tools more precise, and the implications broader than anything astronomers imagined in the 1990s. What began as an unexpected discovery, giant planets orbiting far too close to their stars, has now become one of the richest laboratories for understanding planetary systems. With new observatories coming online, the field is on the verge of resolving mysteries that have lingered for decades while uncovering entirely new ones. The James Webb Space Telescope has already transformed the study of exoplanet atmospheres. Its ability to measure infrared light with extraordinary sensitivity allows it to detect molecules, atoms, ions, and thermal structures at levels unreachable by previous instruments. For hot Jupiters, this means detailed maps of temperature distribution, chemical gradients, and the degree of molecular dissociation across the day side. It means identifying species such as carbon dioxide, sulfur dioxide, and ionized metals, not just in isolation but in context, how they form, how they move, how they break apart under intense radiation. jwst's spectral clarity also reveals how energy flows through these atmospheres. It can distinguish between heat transported by winds, heat absorbed by trace molecules, and heat radiated back into space. These processes determine whether a planet develops a temperature inversion or maintains a smooth thermal gradient. They determine how the atmosphere expands, how quickly it escapes, and how much mass the planet may lose over billions of years. With each new observation, hot Jupiters become more than strange outliers. They become physical case studies for how gas behaves under extreme stellar forcing. Soon, they will have company. The European Space Agency's Ariel mission, scheduled for launch in 2029, will conduct a large-scale atmospheric survey of hundreds of exoplanets. While jwst excels at deep, detailed observations of individual targets, Ariel's strength lies in breadth. It will observe planets across a wide range of temperatures, sizes, and compositions, establishing statistical patterns that can clarify which atmospheric features arise from stellar irradiation, which from interior heat, and which from formation history. For hot Jupiters, this means identifying systematic trends in cloud formation, metallicity, and energy balance. Insights that could reveal which physical mechanisms dominate across different stellar environments. Another mission, ESA's Plato, will provide exquisitely precise measurements of stellar ages and oscillations. Understanding a star is essential for understanding its planets. The radius, mass, age, and internal structure of a star all influence the evolution of hot Jupiters. Plato's asterosismology measurements will allow astronomers to refine the ages of planetary systems with unprecedented accuracy. This matters because many of the processes affecting hot Jupiters, migration, tidal decay, atmospheric escape, operate on billion-year timescales. Without precise ages, evaluating those processes is like watching a time lapse with frames missing. Plato supplies the missing frames. And then there is NASA's Nancy Grace Roman Space Telescope. With its wide field of view and exceptional stability, Roman will detect exoplanets through microlensing and direct imaging, complementing the transit and radial velocity methods that dominate hot Jupiter discoveries. While Roman will not focus specifically on close-in giants, its broad survey will improve models of planetary demographics and formation. Understanding how many giant planets exist at larger separations helps clarify how frequently migration must occur to produce the hot Jupiters seen today. Roman will also refine measurements of stellar multiplicity, whether a star has companions, which plays a crucial role in high-eccentricity migration pathways. Together, these observatories move the field toward a more complete picture of hot Jupiter origins. Each provides a different type of evidence: atmospheric chemistry, orbital evolution, stellar structure, population statistics. The synthesis of these datasets promises to uncover why some planets migrate smoothly through disks while others are thrown inward chaotically, why some atmospheres inflate dramatically while others remain compact, why some orbits align with their stars while others flip entirely. For decades, scientists have tried to fit these planets into a single narrative. The next decade may reveal that multiple narratives coexist. Hot Jupiters also continue to reshape how scientists understand planetary formation more broadly. By existing in regimes far outside what early models predicted, they forced researchers to reconsider assumptions about disk structure, migration efficiency, and dynamical stability. They demonstrated that planetary systems are not static, but evolve continuously through interactions with their environments. They highlighted the importance of stellar radiation, stellar winds, and tidal forces in sculpting planetary outcomes. And by challenging these assumptions, they revealed the need for planetary formation theories to accommodate a greater diversity of worlds. This has implications for every type of planet. Super-Earths, mini-Neptunes, terrestrial planets. Each exists within the broader context of disk physics and dynamical interactions illuminated by hot Jupiter studies. Learning how giant planets move helps explain why compact multi-planet systems exist so frequently. Understanding atmospheric escape helps clarify why Neptune-sized worlds are rare at close distances. Studying tidal interactions informs models of habitability for planets orbiting red dwarfs. The lessons learned from these giants ripple outward, shaping the entire discipline. In exploring these worlds, astronomers also confront deeper philosophical questions about our own solar system. For years, it was assumed that our planetary layout, a few rocky planets inside, gas giants far out, represented a typical outcome. Hot Jupiters shattered that assumption. If planets can migrate inward dramatically, if orbits can flip, if atmospheres can evaporate under extreme irradiation, then the apparent stability of our solar system becomes something unusual, perhaps even precarious. The absence of a hot Jupiter here may have been crucial in protecting the inner planets from chaotic migrations or gravitational disturbances during formation. It is tempting to view this uniqueness as a kind of cosmic privilege, but in reality it is simply one outcome among many. Planetary systems are experiments run billions of times across the galaxy, shaped by initial conditions we barely understand and processes that play out over immense stretches of time. Hot Jupiters reveal how sensitive those outcomes are to the details: disk mass, stellar companions, formation timing, migration trajectories. They show that solar systems like ours may not be inevitable. They may be rare configurations in a universe that embraces diversity far more enthusiastically than predictability. The future of hot Jupiter science is not about cataloguing more of them. It is about using them to refine our understanding of how worlds form, move, transform, and ultimately survive or perish. They are extreme, volatile, often short-lived, but they offer clarity. They turn the violent physics of stellar irradiation and gravitational tides into something observable, measurable, and comprehensible. By studying hot Jupiters, we learn not only what planets can become under extraordinary circumstances, but also what made our own system possible. They show us how fragile the line is between stability and chaos, between a world that remains and a world that migrates inward to be lost. And in that contrast, they help us understand our place within a galaxy full of planetary experiments still unfolding.